let's start. So, make sure, yeah. So good afternoon, everybody. So last time I explained this circuit here. Okay. Yeah. So last time I explained this circuit. Okay. I explained how can you make 4-bit adder. So and subtractor as well. So what this circuit is doing is I have two numbers. I have number A and number B. Each number is 4 bits. Okay. That's why you can see A0, A1, A2, A3. Same thing for B. We have B0, B1, B2, B3. Okay, as you see here. Okay, and then using this circuit, the same circuit can do addition or subtraction. The same circuit. Okay, so yeah. So the idea is that if I put here 0, so here this is B3 XOR 0. We are gonna get B3. Okay, so what these others are going to do is actually it's a summation of A plus B. You add A to B, okay? A plus B. However, if we put here 1, yeah, if I put here 1, so actually these ones are going to be B prime, B prime, B prime, B prime, which is the ones complement. So here, this is the ones, you complement all of them. This is the ones complement. And also you add 1 here. So 1's complement to plus 1, which is the 2's complement. Okay, so what I'm doing here exactly is A plus B prime plus 1. Okay, this is the 1 is here, B prime is here. I flip the bits, and as I told you before, this is exactly equivalent to A minus B, because it's B prime plus 1 is negative B. Okay, so that's what I explained. Also, I explained last time is how can I know if there is an overflow or not? Okay, so here we have two important outputs here. This output is used, this is the carry, this is the last carry, C4. This one is used if you want to know if there is unsigned overflow or not. Okay, very simple. If this one is 1, that means there is unsigned overflow for addition. So here I'm explaining, that's what I'm explaining here. In case of unsigned numbers, if the carry here is in case of addition, so these two for addition, if the carry is equal to 0, so no overflow. If the carry is equal 1 to, so that means there is an overflow. Okay. If for subtraction, if the carry is equal to 1, that means there is no borrow. There is no borrow. Okay. That means the result is correct. And you can see in this example, 9 minus 3, 6. Okay. Here, if the carry is equal to 0, in case of subtraction, this means there is a borrow. Okay. What do you mean by a borrow? You remember in when we do subtraction, you need to borrow. And that's exactly what we did here. So actually, the result I got here is actually 3 minus 9 plus 16. Because the one you borrow here is 16, okay? Because it's 4 bits. When you have 4 bits and you want to borrow, so it's going to be 16. So in general, if you here you have n bits, what you are going to borrow here is 2 to the power of n, okay? Anyway, so, but for this is, so very simple. If your numbers are unsigned, you are going to use C. But if your numbers are signed and you want to know if there is overflow or not, so here, this one is going to tell you V. What I'm explaining, but I'm going to explain now how we're going to calculate this one. As you see here, very simple. We're going to get carry number 4, which is the last carry. We're going to also get carry number 3. So the last 2 carry, okay? And then I'm going to XOR them this way. As you know, in XOR, the result is 1 here if C3 does not equal C4. Okay, the result is 0 if C3 is equal to C4. Is that okay? That means, very simple, if this one is 1, that means there is an there is a signed overflow. Okay, and this happens when the two carries are not equal to each other. Okay, but wait a second. This is not what you told us before. You told us before if you add positive number to positive number, I get negative. This is overflow. Okay. Also, you told us negative plus negative, you get positive. This is overflow. Okay. I just wanna prove to you this is not different from this one, because if you add positive to positive, okay, and you get negative, it will be this case. Okay. Also, it is if it is negative plus negative and you get positive, it will be also the same case. You got what I'm saying? It's the same. To prove to you it is the same, I made this slide here. So if you see here in this slide, it's very simple. Let me explain them to you. I have here, I add two positive numbers. Here also I add two positive numbers. Is that okay? Positive number plus positive number. Now I'm gonna consider two cases. One case when there is a carry coming from here and when there is no carry coming from here. Is that okay? If there is a carry coming from here and 1 plus 0 is 1 and there is no carry here. But if it is 0, 0 plus 0 is 0 and then there is a carry here. Okay, so now let's look based on what I explained right now. If they are different, okay, there is overflow. So this is here, it's not different because here there is no carry coming from here. Also, there is no carry coming from here. So there is no overflow. Here we have a carry coming from here, which is 1 here, and there is no carry over here. So now they are different. That's why there is overflow here. So if you just compare this rule here, if they are equal or not, with what I explained to you before, it will be the same. Look here, this is a positive number. Added to positive number, I got a negative number. Okay, here, positive to positive, I got positive. Is that okay? Okay, let's try the other cases. The other cases is if the two numbers are negative, as you see here. Okay, the two numbers, here I'm gonna add negative to negative. Again, there are two cases. One case, there is no carry coming from here, and there is a carry coming from here. Okay, so just to do the addition, and now you can see here there is no carry, but there is a carry here. So they are different. Because they are different, there is overflow. Compared to what I explained to you before, this is a negative number. Added to negative number, it gives you a positive number. Is that, you understand what I'm saying? So anyway, trying to make it very, very simple. I just want to prove to you these two rules are equal, are the same thing. What are the two rules again for the last time? What I explained to you before, in order to know if there is overflow or not, that's what I explained to you before. Okay, if you add two positive number, you get negative, or if you add two negative number, you get positive. Okay, this one exactly equivalent to if the last two carries are not equal. C3 is not equal to C4. Is that okay? So anyway, I'm gonna leave the rest for you. I took all cases, different cases, okay? Just to convince you, always when you add two positive number and you get negative, you will see the carry is different. Always, okay? Here I add two negative, I get positive. There's overflow. Also, I can see the carry are different, okay? Here, as I said before, you don't need even to think about it. There's no overflow. You don't need to think about it because the two signs are different. Okay, there is no overflow. That's why you can see the two carries are equal. So there is no carry here, no carry, no carry, no carry, no overflow. Anyway, so I don't want to overcomplicate it. Just what I'm saying to make it very simple, to know if there is overflow or not, there are two rules. One rule, what I explained to you before, like this one, or you can look at the last two carries. If they are not equal, that means there is an overflow. Any questions? By this way, this circuit, actually, it can do addition, it can do subtraction for signed and unsigned numbers. Also, it can detect the overflow in the two cases. In case of unsigned, you have to look at the C. Look at this. In case of signed numbers, if you want to know if there is overflow or not, this one is correct. Any questions? Okay. Now, so I have just explained how can you make binary other. That's what I explained. So there is a problem here. I'm gonna try to fix. Okay. So this circuit is working. It is nice. Everything looks okay. You know what's really interesting about this one? As I told you before, this is for if you want to add 4 bit to 4 bit. If you want to add 5 bit, what should you do? Very simple. Just add another full adder. If you want to add 6 bit to 6 bit, you just cascade them. So it's very easy to design this circuit. Okay, you understand what I'm saying? So, however, this circuit has a problem. What is the problem? I'm gonna tell you. Look here. This one, what this other is gonna do is gonna add these inputs here, and then it has to wait. It has to wait until the first one finishes the computation in order to get C1. It has to wait. So they are not gonna work all of them at the same time. It has to wait until the finished one. The first one has to finish to get the carry. So this one has to wait until this carry is calculated. And this carry is calculated after this one is done and this one is done. You get what I'm saying? So make it very simple. So the problem here, this other is slow. Why it is slow? Because every full other has to wait until the carry is calculated. It's slow. You understand what I'm saying? Simply because here, this carry has to be, I can't, this carry has, I have to wait to calculate, to get C3, I have to wait until C2 come here. And in order to get C2, I have to wait until C1 come here. You understand what I'm saying? So this other actually is called carry rebel other, because the carry rebels, propagate, the carry propagate. Any questions? You understand what I'm saying here? So this one is nice, everything is okay, but it has the problem that the delay is long because I have to finish. Everyone has to wait until this carry is calculated. So this one can tell to give you the final answer until all of them finish. So it's like they can't work in parallel. It's not by line. They're not going to work at the same time. So that's what I want to say. Any questions? Okay. Now, okay. So how can we improve this one? We're gonna redesign the circuit, okay, so that we can solve this problem. I'm gonna tell you here. Okay? So keep in mind that's always how it is. It's not only in logic circuit, everywhere. Nothing is for free. If you want to make the circuit fast, you have to pay the price, you have to pay the cost. And what I mean by cost here, the circuit is going to be more complex, as you will see right now. So I have to add more hardware. Nothing is for free. Okay, that's exactly what I'm doing. So so now I'm gonna design a new adder. This new adder, I'm gonna solve the problem we had here about waiting for the carry. So to do that, we are gonna design a circuit. Look here. We are gonna design a circuit. This circuit is called carry local head generator. What this circuit is gonna calculate all the carries at the same time. Look what's gonna happen here. So you have some inputs here, and then after one propagation time, all of them, and then after a second propagation time, you are gonna get all the carries. You are not gonna wait. So just you need to wait for 2 propagation time, and then you are gonna get all the carries you need. So I don't need to wait. So what was the problem here? The problem again was to get this carry, I have to wait until this one come here so that I can get this carry. You got what I'm saying? We're gonna design the circuit to avoid this problem. But how you are gonna do it? I'm gonna tell you how. So this is the same circuit I had here for other. If I go back here, yeah. So this is the full adder. When I explained full adder, I told you the full adder can be designed this way, or I can design the full adder using 2 half adders. So this is half adder and this is half adder. Is that okay? So I'm gonna show you now how can we calculate all the carries at the same time without waiting okay, for the calculation of the previous carry. You will see right now. So I'm gonna take this circuit here. So this circuit, again, this is just one full adder, right? So here we have multiple full adders here. So I'm gonna only talk about one for now. So this is one full adder is here. So I'm gonna call here, this is the input AI and BI, 1 bit and 1 bit, because if you see here, every adder, it has only 1 bit here and 1 bit here. Okay, for sure this is a carry, and the output is the summation and the and another carry here. Okay, so here I'm gonna call it AI and BI. Okay, and then the output of this one here, I'm gonna call it BI. Just I'm gonna use different names than I used to before for a reason. You will see now. So here this one is BI, and BI simply is the XOR between AI and BI. You understand what I'm saying? So here, why I use subscript I here? Because the same circuit can be used when I is 1, when I is 2, when I is 3. Okay, for any one. Anyway, so here this BI can be calculated this way. I'm gonna call this one GI. So GI is actually AND AI and BI. GI. Is that okay? Now my problem is here. Okay, let's calculate this carry. Okay, this is the carry I plus 1. This is the next carry, or the carry generated from this one has to be input for the next full adder. So this carry is resulted from, we have OR operation here. GI is coming here, GI, as you see here, GI, or the output of this AND, which is PI, okay, and this one CI. So this is the relation for the carry. So again, I didn't do anything new until now. Nothing is new. All what I did, I just used different symbols for a reason. But this one is similar to what I explained before. So now, CI plus 1 equal BI and CI or GI. So every carry, in order to calculate a carry, I need to calculate the previous one. And this is the problem. So this is the problem here. So this equation is iterative equation. So here, every carry, in order to calculate a carry, I have to calculate the previous one first. And this is a problem. That's what I want to cancel. That's what I want to solve. I want to calculate any carry without. So it's like I'm gonna calculate a different value for CI plus 1. I want to get rid of this one. I don't want this CI plus 1 to depend on CI because I don't want to wait. You know what I'm saying? So all what I did, very simple. Look what I did here. What I did here is, okay, very simple. Let's calculate CI and just plug in here. Okay, so let's start with, for example, for the first one. For C1 is actually the carry here, the first carry here, okay? So, and then I'm gonna calculate C1, and after I calculate C1, I will try to calculate C2 without the need for C1, because I don't want to wait. This is exactly what I'm gonna do. So all what I'm gonna do, I'm gonna do just some manipulation to the equation to get rid of CI, so that I'm gonna have one equation. I can just use it to calculate the carry. That's what I want to do. Okay, you will see right now how I made it. Very simple. So based on this equation here, okay, so C1 is equal B0 C0 plus G0. Is that okay? P0, this one is P0. B0 resulted from A0 and P0, which is the first full adder. Anyway, so we don't have a problem with this one. So this one should be okay, because this carry C0 is input. I'm not gonna wait for C0, it's input. Okay, so this one should be okay. The problem will come here. The problem now, and this is the interesting part, look here. C2 should equal P1, C1, or C2, and this is the problem is here. I want to get rid of C1. Okay, so all what I'm gonna do, very simple. All what I'm gonna do, I'm gonna replace C1 by this equation here. That's it. if I do that, C2 should equal, so that's all what I did. So what I did, this is C1. I'm gonna take this one, just put it here. Okay, and then do the just do distribution. That's it. Okay. So if I do it this way, so now C2 is actually function in C0, which is the input. It's not a problem for me. P0, P1, and G1. So now this equation does not have C1, which is great. Let me say it again. Very simple. So the problem is here for C2. Okay. The problem, I have to wait until I hit C1 to do this calculation. So all what I did is C1 is equal to this one. So I just take this one, plug in here. Once you plug in here, I got, now I can calculate this carry C2. I can calculate C2 without waiting for C1. If you have P0, P1, C0, P1, G0, G1. And I can get all of them at the same time. I can get them without waiting for the carry. So that's exactly what I did. I was able to get the carry without waiting for the. So this equation is similar to this equation. The difference is I just this carry does not depend on the previous carry. So I just replace it by it's there. Okay. So if I could, this is so here. So if I could, this is for C1. Okay. This is for C2. It's gonna become this way. I can do the same thing for C3. So based on this equation, C3 is equal, okay, P2, C2, okay, or G2. And then all what I have to do, I'm gonna replace C2 by this one here. And that's what I'm gonna get, C3. So that's what I'm gonna get here. You understand what I'm saying? So I just did simple manipulation so that the equation of C2 does not depend on C1. There is no C1. C3 doesn't have C2. But it has P1, P0. It's just a function in Pi and Gi in general. This is not a problem. Why? Because I can generate Pi and Gi, all of them at the same time. So I don't need to wait for them. Okay, I'm gonna tell you how. Or very simple. So as you see here, this is Pi and Gi. Okay, so I'm gonna use. Let me come here. So look what I did here, guys. Here I have B3, A3. Then I'm gonna use these two to generate B3, G2, B2, G2, B1, G1, B0, G0. Because all the carry in this circuit is called carry look ahead generator. Okay, so here this circuit, the input of this circuit is actually Bi and Gi, Bi and Gi. The output all carries at the same time. Okay, all the carries. I don't need to wait. Okay, all what I need, very interesting here, because this is gonna be fast. Why this one is fast? Because just all of them are gonna work at the same time. I'm gonna work. They are not series. They are not series, so they are gonna work at the same time. I'm gonna wait for one propagation time and then a second propagation time. These two are gonna work at the same time. Okay, so just I can generate all the carries just very quickly. Okay, but to do that, I need to calculate. I need to get Bi and Gi. This is not a problem. I can get Bi and Gi, all of them at the same time, and that's what I did here. So if you look at this part here. If you look at this part here, all what I did here, I took this one, I took this part from the full adder to generate Bi and Gi. Okay, that's exactly what I did here. So all of them are gonna work at the same time. So when you have input here, okay, so just you are gonna wait one propagation time, and then you are gonna get B3. So I'm gonna get Bi and Gi, all of them. Is that okay? Once I get them, all Bi and Gi, I'm gonna input them. The look ahead generator, which is this circuit, so I can input all of them here. By this way, I can get all the carries. Okay. So after I get all the carries now, I have all the carries. So what is left now? What is left now is the summation. How can you get the summation? I'm gonna go back here to show you the summation is actually XOR of PI and CI. So once you have the carry, all what I need to get the summation, I need to XOR BI with CI. That's it. Okay. So, and that's exactly what I did here. So if you see here, S3 is actually C3 XOR B3. S2 is actually XOR B2, C2, and so on. For sure, this circuit is more complex. That's for sure, but it's faster because the carry is not going to depend on another carry. Okay, how it works? I'm going to tell you how it works. This is the input. So I need propagation time, one propagation time. So all of this can work at the same time, and then I'm going to get all B and G. Okay, and then all B and G are going to go here, input here for this circuit. All of them are going to be input here. Now I need to wait for two propagation times, one for this one and another for this one, because all of these are going to work at the same time. That's okay. After that, I got all the carry. And then after that, I'm going to wait for one propagation time here to get the result. Any questions? So this one, for sure, it's more complex, but it's faster. And this one is called other carry look ahead other, or CLA. So now I explain two different others. The one is called carry rebel other, CRA, and then the other one is called carry look ahead other, CLA. Again, the main idea is very simple. I'm gonna make a circuit here, logic circuit, so that I can calculate all the carries at the same time. Any questions? Okay. So I am done with the binary other and subtractor. So now, because I need, I'm going to teach everything for sure in the slides, but I need to start with the topics I need for labs first. That's why I'm going to skip these two. I'm going to come back to them, but I'm going to skip these two. I'm going to go to decoders and encoders. That's what I need in labs first. Any questions? Okay, so look here, guys, it's very simple. So for other or subtractor, it's a circuit, logic circuit. As I said, this logic circuit, it has, for example, 4 bit for A, just an example, 4 bit for B, and then this one is gonna give me 4 bit for the summation, give me a carry. That's it, okay? This is as a black box, okay? And then I explain how it looks like from the side, how it looks. Same thing I'm going to do right now for other, for decoder. So what is decoder? Okay, how it looks like, and how we're going to design it. So let's start with the definition of the decoder. Okay, look here, guys. Decoder, you have, let me give you just, for example, one example here. In decoder, this one is called 2 to 4 decoder. Okay, what 2 to 4? It means we have 2 inputs and we have four outputs. 1, 2, 3, 4. Okay, it's called 2 to 4 decoder. How it works? How this one should work? That's what I'm going to tell you. Look here. The idea here is that I have here two bits at the input, and usually at the output I have 2 to the power of 2, which is equal 4. So in general, usually if you have n bits input, the output is actually 2 to the power of n. Okay, so look how it works. If you have here, this is the input. For example, I'm going to call it AB. So all possible cases for the input, it can be 0, it can be 1, it can be 2, it can be 3. Okay, this all possible cases for the 2 inputs here. Okay, now I have 4 outputs here. Okay, this output, I'm gonna call it output 0, output 1, output 2, output 3. Okay, how it works? I'm gonna tell you how it works. Very simple. If the input is 0, 0, 0, which is in if you convert it to this 0, so what's gonna happen? this one here, this pin, the pin 0 is 1, and the other pins are zeros. To indicate, to tell you, so I have four pins. If the input is 0, this one is 0, the other ones, this one is 1, the other ones are zeros. Okay? If the input is number 3, so this one is 1, all of them are zeros. Okay? So here again, the input is a binary number. Okay? This binary number can take from 0 until 3. The output here, we have four outputs. If the input is 0, so this output is 1, and for sure the other should be 0. If the input is 1, so this one is 1. So very simple. So the output should tell you what is the value at the input. Very simple. You understand what I'm saying? How it is. This is how it works. Okay. So how we're gonna use it, how it is useful, is a different issue. Now focus on making a definition. The definition is a decoder usually has n bits and the output 2 to the power n. Okay. Number 2, based on what the number you have here, the corresponding output here should be 1 and the other one should be 0. Is that okay? Yeah. So here for decoder you have n inputs, n bit inputs. We have m output, and usually this m is actually 2 to the power n. Okay? They have to be 2 to the power n in most cases. So 2 to the power n is going to give you all possible cases here. This was for n. Anyway, so let's start with the design of the first one here. How I can design a circuit here to do what I've just explained right now. What circuit I have to put it here? Okay. So let's look at the truth table here. This one is called 2 to 4 decoder. You can tell from English name why I call it 2 to 4, because the input is 2, the output is 4. Is that okay? So this is the truth table is here. The input here, it can be 0 or 1 or 2 or 3. The output here, this one I'm gonna call it D0, D1, D2, D3. Okay. So which one should be asserted? Asserted here in this case high. Which one should be high? Based on the input. If the input is 0, so this guy is 1 and everyone else is 0. To tell you the input is 0, right? When the input is 1, so D1 is 1 and everything else is 0. If this number, what this number is? 2, right? This number is 2. So number 2, 1, everyone else is 0. This number 3. So number 3 is 1, everyone else is 0. You understand what I'm saying? So the output can tell you what is the number in the input. Okay. Any questions? Okay. How can we design this circuit to do that? What should be inside here? Okay. It's very simple. Let's see how I'm gonna design it. Okay. If we start with D0 here, D0 has to be 1 when the input is 0, 0. Anything else, it has to be 0. Very simple. If you look at the truth table of this one, very simple. There is only one case. D0 has to be 1 when the input is 0, 0. How I can do that? Very simple. So here in this case, D0 should equal A1 prime, A0 prime. So that when 0, 0, okay, 0, 0, the result here will become 1. Because here, this is 0, inverter, you get 1, and 1, the result is 1. For this specific case. If you check any other case, this one is going to give you 0. So all what I need just and gate. Okay? And that's exactly what I need. So this is AND gate for these 0. This AND gate is taking A prime, A0 prime, A1 prime. So that this one is going to be 1 in this specific case. In any other case, this one becomes 0. You understand what I'm saying? What about the other ones? Same thing. I'm going to just repeat it. Look here. Look, let's design the next one. D1 is going to be 1 in only one case, which is this one here. So that means D1 should equal, okay, A1 prime and A0. So again, look here. If this is 1, I'm going to keep it. But if it is 0, I need to get the prime because this is AND. For AND to get 1, all the input should be 1s. So whatever 1s, I'm going to keep it. Whatever 0, I'm going to flip it. So that's why here you can see D1 should equal E1 prime is 0. Same thing for the other one. So if I come to this one here, D3. So D3, simply I'm going to make it using AND gate, and then I'm going to put here A0, A1. This one gives you D3. Very simple. So this one will give you 1 only in one case, when the two inputs are 1s. Any other case you can see. Any questions? So now I'm expecting you understand. Number one, what is decoder? What this circuit is doing? Okay, very simple. So based on the number in the input, one of the output. So every case in the input, every case of the input, it has one output, one line is out, right? And if this is the number, this one should be 1 and the other one should be 0. Okay? Any questions? Okay, now I want to do a simple modification to this decoder so that I want to add an enable bit. And this is something very common. We do it all the time in digital circuits. Usually in digital circuit, I want to add like a switch. Okay, you want a circuit to work or doesn't work. That's what we put by enable. So usually in digital, we like to do something like that. So here it's exactly the same thing I explained to you before, but I just want to do a little modification by adding what we call an enable. So what this enable is doing, I'm going to tell you what it's doing. Very best in order to understand how it works, the truth table can help you. Okay, let's look here. This is the enable is here. If the enable is 0, that means the set. I'm turning it off. I'm turning the decoder off. I'm disabling it. It doesn't work. Okay, what it means, it doesn't work. So whatever, look at the truth table, it's going to tell you if the enable is 0. So whatever you put here doesn't matter. So whatever input you have, all the outputs are zeros. That's what's the truth table, because it's not working, because I turned it off. So look at the truth table here. So here I want to add an enable. This enable, if you put 0, that means you disable or you turn off this decoder, which means when you turn off, it's not going to work. So if you add here number 1, you are not going to see 1 here as usual. This is the normal operation. It's not going to be, it's going to be zeros regardless of what input you have here. It's not working. You turn it off. Is that okay? This is the meaning of enable bit. Okay. Now, if the enable is 1, so now it's going to work as normal. If the enable is 1, as you see here, as normal. So if the input is 0, D0 is 1. Okay. And if the input is number 1, so actually D1 is 1. This is the normal operation. So here this is the normal operation. If it is number 2, so here D2 is 1. If it is number 3, D3 is 1. The normal. You got what I'm saying? Any questions? X, don't be confused. XX here means whatever value you put. It doesn't matter. 0, 0, 1, 0, whatever you put. Okay. So now let me ask you a question. Very simple question. This is the previous. This is without enable. Look here, guys. This is without how I can add enable here. How I can add enable. Remember. For AND gate to get 1 here, all inputs have to be 1s. That's how AND gate works. So, and I'm gonna do very little modification to this circuit so that I can add the enable. You know what I'm gonna do? I'm gonna tell you. All what I'm gonna do, I'm gonna just add 1 input here and 1 input here, 1 input here, 1 input here, and I'm gonna call it enable. Done. Very easy. But how? Very simple. If this enable is 0, all the AND gates are going to give me zeros. That's okay? And so 2 things here, guys. If you have here AND gate, 0, and then if you have, for example, x, y, for example, x and y, you'll get 0 regardless of anything, okay? But if you have here 1 and you have here x, y, I'm gonna get x and y. This is how AND works. And that's exactly what I did. So what happens here when the enable is 0, so all, it's like you shut down all of them. All of them are off. And then you are gonna get, is that okay? There is another way to explain this decoder. I can explain this way. When the input is 0, 0, so actually you turn this one on so that you can get 1 here, and the other ones are zeros. So because for the other ones here, for sure, one input should be 0, for sure. Okay, so I'm gonna get 1 here. Okay. So however, for this input here, number 1, this one is on, but the other ones are off. Off here means they are giving 0, so I input 0. That's what I mean. Okay. For this one here, so this is the one that's gonna give you 1, and the other ones are, they have one input is 0. Okay. Any questions? You understand the idea of enable, because we are gonna use it all the time. We use it all the time in logic circuits or in circuits. You have 1 bit enable. It's like a switch. Do you want to normal operation, or you want to turn it off? Okay. That's what I did. I just added. Any question? Okay. There is also something you should understand. Sometimes if I bring a decoder this way and I see enable this way, sometimes they put a bubble here, and they tell you this is an enable. What is the difference? This is something general. We use it in many, always we use it all the time in digital circuits. Okay. So what is the difference? This one is called active high. This one active low, because there is this bubble usually means invert. Bubble means there is an invert. So this means if you see something like that, that means if you want to enable, in this case, you have to input 1. But if you need to enable here, you have to input 0, because this inverter is going to make it 1. Got what I'm saying? So again, I can design the circuit in 2 different ways. One is called active high, active low. Right? In case of active high, I'm going to make enable when you input 1. In case of active low, I'm going to make it enable when you input 0. You got what I'm saying? Okay. So how I can modify this circuit so that this one is active high, right? If I input 1 here, it's gonna work active high. How I can make this circuit little bit modification on this circuit to make it active low? You know what I'm gonna do? I'm gonna just put inverter here. That's it. That's it. So that when you input here 1 means disable. So the inverter is gonna make it 0 so that all of them are off. Okay. But if you input 0, it's gonna work. So it's gonna work 0. It's gonna be, that's why it's called active low. It's active when it's 0. You understand what I'm saying, guys? So again, very important, when you see enable this way, it's different when you see enable this way. You understand what I mean by active low, active 0? Okay. Okay. There is one thing also, so that's what I'm explaining here about it. When you put a bubble here, when you see a bubble here, it means it's active low, 0. Okay, so it's gonna enable by 0, not 1. Okay. Some decoders, I can also make the output here active low. The previous one here I explained, it was active high. So what it means here, this one. So again, I'm comparing this case with another case when you have bubbles here. So what is the difference? I'm going to tell you the difference, okay? This one is active high. What it means? It means, look at the 2 steps. It means when the input is 0, so this 0 is 1 and the other ones are zeros. Okay? So 0 means it's not selected. So 0, it means this input is not, the input is not 0, right? Now, if I put bubble here, I'm gonna make the opposite here. Opposite means if it is 1, that means it's not selected. So only one of them is 0. And if the one that is at the input, okay, the number that is the input should be 0, and everything else is 1. Again, it's just a different design. Sometimes we need this one, sometimes we need this one. I'm not telling you, I can't tell you this is, I'm not comparing. It's not about comparison, which one is better. No, you have this one and you have this one. It depends on your circuit. Do you wanna, when you enable, do you need 1 or 0? Okay. So again, what I'm gonna do right now, guys, I'm gonna make another modification for this decoder so that I'm gonna put bubble here. So when you see bubble here, it means if the input is 3, so the 3 is gonna be 0, not 1, and everyone no, it's gonna be ones. Gonna be the opposite of what we did here. And yeah, so that's why, look at this one here. That's how it looks like. So here there is another decoder. This decoder is called active flow enable. So the enable is active flow, as you see here, okay? And the active flow output, the outputs also are active flow. Look at the truth table here. It's a truth table here, as you see here. When the enable is 1, it means it is disabled. When it is disabled, all outputs are 1. So 1 means it's not selected. Okay, 1. But if the enable is 0, that means it's gonna normal operation. Okay? And then after that, if the input here is 0, D0, look here, D0 is 0, and everyone else is 1s. When the input here is number 3, so D3 is 0, and everyone else is 1s. You understand? So I just flip. Okay. Again, don't tell me which one is better. No, we have this one, we have this one. This is decoder, this is decoder. And then when you design your circuit, you can select either one of them. This is what you want to do. You understand what I'm saying? So both are okay. No one is better than the other. So now, what it change I have to do for this circuit in order to do this one here? Very simple. The change I'm gonna do, I'm gonna just flip the output here. So I'm gonna put here inverter. So, or you can just, instead of using, so again, you can simply, you just put inverter here. So if you put inverter here, it becomes active low. Okay, without inverter, active high. Very simple. Similar to what I did for the enable here, I put inverter. Same thing here, I can put inverter. And as you know, if you have AND and then inverter, that's what we call NAND. So, okay, that's why here, that's exactly what I did. So what I did here, I just used NAND. Okay, any questions? To make it simple, what I did here, this is the basic, or this is the one I explained, and then I did 2 modifications to this one. What I did, I just put here inverter here at this at the enable, and by doing that, it's gonna be active low enable, active low. Same thing here, I'm gonna put inverter here, so that all of them, if you select number 3, for example, number 3 is gonna become 0, and everyone else is 1s, not 0s. Yeah. Any questions? Okay. So this inverter, sorry, this decoder is 2 to 4. Input is 2, output is 4. Okay. Can I design one that's input is 3? Yes. If the input is 3, how many outputs I need at the output? How many outputs? 8. 2 to the power of 3, because I have 8 numbers, right? That's so I'm gonna show you. I'm gonna exactly same way. See, everything almost the same. Just if everything is the same, you are going to use one AND or one NAND in this case, okay? For every output. So if you have 8 outputs, I'm going to use 8 AND, okay? As you will see here. So this is 3 to 8 decoder, okay? The input is 3. The output is from 0 until 7, because in the first class or second class, I told you if the input is n bits, output should be 2 to the power n. So in this case, I have 3 bits input. So in 3 input, you can have a number from 0 until 7. Okay, I'm saying? So if the number here at the input is number, for example, number 5. So pin number 5 should be 1, and everyone else should be 0. That's it. Very simple. Okay. So look, this is exactly the truth table. If you see the truth table here, this is 0. This is the input is 0. That's why we have 1 here. This is the input of 4. So this is 4, right? So that's why you see here, number 4 is 1. This is the input for 7. Only here 1, 7 is here. Only one output is 1, and all the others are 0. Is that okay? Okay. How can we design it? How can we design this one? Similar to what we did before. Let's do it. For example, let's do here, for example, for D0. D0, okay? So here it has to be an AND this way. We have 3 inputs, and this is D0, okay? I want a D0 to be 1 only in one case. Only one case. If you look here, every other case is 0. Only one case. When the input is 0, 0, 0. So here I'm gonna, when the input is 0, because this is AND, the AND gives me 1 when all inputs are 1s. What I'm saying? That's why if the input is 0, I'm gonna complement the input. If the input is 1, I'm gonna keep it. Okay. So that's exactly what. Because here the input is 0, 0, 0. So actually I'm gonna say here X prime, Y prime, Z prime. That is very simple. Let's take another case. For example, if I take this case here, which is D3. So here we have here D3. Okay. Okay, look here. Y is already 1, so I'm gonna put Y. Z is already 1, so I'm gonna put Z. Okay. X is 0, so I'm gonna say X prime. That's it. So in this specific case, this AND will give me 1. All other ANDs will give me 0s. So I'm gonna make 1 AND for this specific case. Okay. Any questions? So that's how it looks like. So I need to use 8 ANDs, as we see here. 8 ANDs. For every D, I'm going to use 1 AND. And look here, this is prime. So this is equivalent to 0, 0, 0. So this is prime. So this is 0, 0, 1, which is number 1. Okay, this is 0, 1, 0. So anything that's prime, that means it's going to be activated, or the output here is going to be 1 when this one is 0. So 0, 1, 1. Okay, and so on. Any questions? Good. I'm not gonna follow exactly same. I'm gonna explain everything. That's usually what I do, but I'm gonna just skip some parts. I want to explain this part first. Okay. So now I explained decoder. You understand what is decoder? We already designed. So you understand the truth table, and we designed it. Okay. So the design is, if you have 100 outputs, I'm gonna have 100 AND gates. Okay. And the AND gates are designed so that only one of them gives you 1 in a specific case, all the other ones give you 0. Okay. That's how it is. So here, because that's what we need in the coming lab, okay, here I'm gonna explain to you one of the ways to use very interesting way to use decoders. Okay. I'm gonna tell you what is this, and very interesting. Let me see, find that. Okay, look here. For a decoder, for example, if you have 2 to 4, so here we have 4 outputs. This is output 0, 1, 2, and 3. Is that okay? So this one active, remember, this one should be active when the input is 0. On other words, when the input X prime, Y prime. Is that okay? This one should be active when the input is 1, which one is actually X prime Y. This is 1, right? number one. Number two, it is x, y prime. Okay, number three, this should be x, y. Is that's what I explained now. When the input x, y, okay, or when the input 1 and 1, okay, which is represent x, y, so this one should be 1, okay? So now, what are these? What are these? Remember what I did in chapter 3. These are actually the min terms. Min terms. Let me go to chapter 3. Here. Yeah, if you look here, M0, the midterm 0, x prime y prime. Midterm 1 is x prime 1, right? So M2 is actually x y prime. M3 is x1. The midterms. Okay. So same thing if I go to for in case of three variables. In case of three variables, it's the same thing. Okay. So here M0 is actually x prime y prime z prime. Which is, this one is going to be the first output in the decoder. What do you want to say? What I want to say is the output of the decoders are the min terms. What I'm saying? In other words, if the input is 0, so I have one output, then give you 1, which is this one. If the input is 1, I have one output, give you 1. Is that okay? This is number 1. So the first thing you should understand, the output of the decoder is min terms. Second thing, as I explained in this chapter and also in chapter 2, any function is the summation of min terms. You remember when we said, that's exactly what I did in chapter 3. You need to, yeah, for example, when I say this function is the summation of min term 1 and min term 2. Summation means all. Okay, so what do you want to say? What I want to say is, this is a conclusion before I give you more details. What I want to say is, a decoder can be used to implement any functions. Any function can be implemented using the decoder. Why? Because any function can be represented by summation of min terms. And the decoder is going to give you all the min terms, and you select whatever you want. You understand what I'm saying? I'm going to give you more details to understand what I'm saying. So anyway, so there are now okay. I'm gonna summarize what I said now, guys. Number 1. The output of the decoder is actually the min terms you have. So in case I have 2 inputs, so in case of 2 inputs, I have 4 min terms. It's gonna give you all the min terms. That's what you should understand. Is that okay? Min term means this is gonna be 1 when it is x prime 1, x y prime. Min terms, right? Again, this is how this course is. What explained is the first time I'm gonna use it all the time. So I already explained min terms before. Okay, but that's how it is this course. Anyway, so this is number 1. So you have all the min terms. You have min term 0, min term 1, 2, and 3. We have them. That's number 1. Number 2, any function is actually the summation of min terms. That means I can implement any function using a decoder and the OR gate to do summation, OR gate. So if your function, it has min term 2 and 3. So I'm going to take 2 and 3 and I'm going to input them to OR gate. And this can implement this function. Okay? Let me give you several examples here to this idea. Okay. Yeah. So this is the first example we have here. I want to implement a full adder. I want to implement a full adder using a decoder. Okay. So this is the truth table for the full adder. These are the inputs here. We have 3 inputs, and the summation. We have summation and we have carry. That's what I explained to you before. If you just do, I don't want to repeat, but that's what I did before. 0 plus 0 plus 0. Okay. The result is 0. Summation is 0. Carry is 0. 1 plus 0 plus 0. 1 and 0. So this is the full adder I explained to you before. I'm going to show right now how can we implement this full adder using a decoder. That okay? So number one, which decoder do you need? For sure, I need 3 inputs in the decoder because I have 3 inputs here. If you have 3 inputs, so I need the decoder should have 3 inputs. So 3 to 8. So I need 3 to 8 decoder. So I have 3 inputs and 8 outputs here. This one. Okay, this number one. Number two, if you look at this one here, for example, look at the summation. The summation has to be 1 in this case. Also, it has to be 1 in this case. Also, it has to be 1 in this case. Also, it has to be 1 in this case. These are the main terms. So all, and this one is actually given to you. This is given to you in number 1 here. Okay. So this pin in this specific case, this one is 1. In this specific case, number two here. So this is actually min term number 1, 2, and this one is 4. This is number. That's why if you look here, so I can say the summation is sum is actually the min term is 1, 2, 4, 7. So this is 1, 2, 4, 7. Okay. That's what I did. So very easy. All what I did is I got the input. The min term is 1, 2, 4, 7. 1, 2, 4, 7. I'm gonna input 7. I'm gonna input all of them to 1 OR to get summation. Okay. Same thing for carry. If you look at the carry here, the carry has to be 1 in this case, has to be 1 in this case, it has to be 1 in this case, it has to be 1 in this case. So all what I need just OR gate, okay? And so this is actually the summation of what are the min terms here, okay? This is number 3, is that okay? 5, right? And 6 and 7, okay. So if any one of these min terms is 1, the output has to be 1. That's why I'm gonna connect this one here to number 3 and 5, 6, 7. Okay, any question? So now what I explained before I take this question, what I explained now is using a decoder and the OR gate, I can implement any function. Yes. What if you wanted to show the neighbor? What? Show the neighbor? Yeah. No. Enable the decoder itself. You can have an enable, right? Yeah. So here I'm not designing a decoder. I already have a decoder. Okay. So the decoder itself, it can has an enable. That's true. So in this case, if the decoder has an enable, that means if you disable the decoder, you disable the circuit. The circuit is not working. If you enable the decoder, it's gonna work. Any question, guys? Let me say it in a different way quickly, just in case you didn't fully understand it. Let me explain in. So here, when the input in this case, 0, 0, 1, 0, 0, 1, okay? What's gonna happen is this output is 1, and then I'm gonna get 1, yeah? And this is the case here. There is another case when at this input, I need to generate 1 at the output. At this specific input, I need to generate 1 at the output. Or at this one, I'm gonna, that's why I'm using OR. Because or if one input is 1, I'm gonna, so in case of when this one is 1, I'm gonna get 1, which is this case. When number 2 is 1, I'm gonna get 1. Okay? Which is this. Any questions? I think I have another example here. Okay, it's not an example. It's just a twist. Okay, so look here, guys. So when I say the min terms for the summation 1, 2, 4, 7, what it means? It means if in case of min term 1, min term 2, min term 4, min term 7, is that okay? The output has to be 1. What about the other min terms? If any other min terms has to be 0. So this is how this function should work. So this function, this is how it should work. In case of this min terms, this one's here, it has to give me 1. What about the other min terms here, which is the remaining one, which is min term 0, min term 3, min term 5, min term 6. the other ones here. In case of this other one, it has to give me 0. Is that okay? Okay. That's the meaning of it. When I have any of these main terms, I should get 1. Any other main term, I have to get 0. Is that okay? Look at this. Now, sometimes it may be more efficient for me to design this one using NOR instead of OR. Look what I'm gonna do. What I'm gonna do is so now I can say S equals this one. I can also say S prime, which is 0, okay, should equal the summation of 0, 3, 5, 6. That means, what this means? It means the function should be 0 in this case, okay? So if S equal 1, 2, 4, 7, so S prime has to be 0, 3, 5, 6. That means if the complement of S, which is, what is the complement? Which is the 0, this case, this one. Is that okay? So now, what I want to say is, when you do this implementation, you have 2 options. The first option, like what I explained here, you can use this one. The second option, I can use this one, 0, 0, 3, 5, 6. But in this case, I have to use NOR instead of OR. Okay? Because if you use OR, this will give you S prime. When you use NOR, the inverter is going to convert it to S. So let me say that in a different way. So what I'm saying here, guys, is if I take here number 0 and then number 3, okay, and then number 5, and then number 6. If I do OR, so I'm going to get S prime. So if any one of these is 1, so if you select any one of these, that means it's S prime is 1. S prime is the inverter of S. Okay? Because S has to be 1 only in this case. This case, any other case has to be 0. So in other words, in any other case, S prime has to be 1. S prime. Okay? Anyway, but if I put here NOR gate this way, this one becomes S. Okay, so what is the conclusion? What I want to say is, this is the final conclusion. The conclusion is, if you have the main term this way, for example, if you have here, this may be just an example. If you have S here is equal to the summation of 1 and 2, for example. So that means S prime is actually the summation of 0, okay? And then 3, 4, 5, 6, 7. Is that okay? So that means I have the option, I can use OR here, I can use NOR here. That's what I explained. But which one is efficient? This one is more efficient. Why? Because this one has a smaller number of main terms. This one here, it has only 2. But this one has 7 main terms or 6 main terms. So this NOR gate has many inputs. You understand what I'm saying? So conclusion. When you have the option, so now I can tell you the opposite. The opposite is if this one, if you have here, so again, what I explained is there are two ways of the implementation. One way to use this one and then use OR. Okay. The other way is you can use NOR and you can use the remaining main terms. Okay. So for efficient implementation, try to select the smaller ones. If this one is smaller, okay, just use OR and that's it. If this one is big one, so you can use the remaining ones. Okay. So you can implement S prime, and then because this one is NOR, it's going to make it S. Any question? Actually, in this example, it doesn't make big difference in this example because if you implement using S or S prime, in both cases, it's four main terms. So regarding efficiency, there is no difference because this is 4 and this is 4. Okay? So if you use OR or use NOR, you are not gonna see more efficient. However, if one of them is small, the other one is big, so try to select the small one. Any questions? Again, because I feel like still some students are confused here. What I'm saying, guys, very simple. When you have, for example, let's talk about the carry here. This is the carry. That means if I can implement this one using C, okay? And then I'm gonna input, this is sum of product I explained in chapter 2. And then I can put here the main term is M0. I can put the main term M5, M6, M7. This is one way of the implementation. If you take the other terms, or the other terms like 0 and 1 and 2 and 4. So if you take these other terms and if you input them to OR, okay, you are gonna get carry prime. You are gonna get the complement of the function. If you input the other ones to OR. But if you put it NOR, you are gonna get C. Any questions? Okay. So last thing I want to explain here, which is also related to this one. So I have explained if the decoder is active high, this one is active high because there are no bubbles here. This one is active high. Active high means this one is going to give you the main term. So the input is 1, this one is 1, the main term. Okay. What if my decoder is active low? How I can implement the function in this case? It is active low. Okay, that's what I'm very simple. So in case of active low, as you see here, 0 is gonna give you the complement of the main term, not the main term, complement. Okay, because you have inverter. Okay, so M1, this one is actually the complement of M2. So very simple. So what I'm saying here in this decoder, you don't have the main terms, but you have the complement, the main terms. Okay? So all what I'm gonna do very simple trick. If this function is actually M1 or M2, M3, so that's what I did in the previous case because I have the main terms themselves in the previous case. Now I have the complement of the main terms in this case because this decoder is active low. Okay? So I'm gonna do a very simple trick here. Okay, so actually, if I use De Morgan, I can see this one is equivalent to this. Okay, just apply De Morgan. If you apply De Morgan, this one here is gonna cancel this one. It's gonna cancel this one, and this end becomes OR. Okay, so this one. So all what I'm gonna. So here, that's what I'm saying here. If the decoder is active high, you can do this way, and that's what I have just did right now. Okay, just use OR, and then you put the main terms. But in case of when it is active low, you don't have main terms. I have the complement of the main terms. Okay? That's why I can. What is the relation here? It is name. So all what you have to do here, instead of using OR, I'm going to use name. Okay? So for example, if I want to implement this function has to come from 1, 2, and 4. So I'm going to come to 1, 2, and 4. And instead of using OR, I'm going to use name. Okay. Another function here, 4, 7, 9. So here, I'm going to use 4, 7, 9. And instead of 4, I'm going to use name. Okay. Because here in this case, I don't have the main terms. I have the complement. Yes, what's your question?
I was going to ask, since you're using NAND for the invert 7 max.
Yeah, this is a very good question as well. Okay, so similar to what I did before, yes. So what I did before here, I used OR, and I told you if you want to use the max terms, you have to use NOR. That's what I did. Okay, so here you are right. So here, if I use NAND, so now you need to use the main terms. If you want to use the max terms, so yes, you have to use AIM instead of NAND. Yes. Any questions? Because very simple. Because if you use, for example, F1 prime, okay, and if you use here NAND, So if you use NAND and use the other terms, this one give you F1 prime. Okay. In order to get F, you have to put another inverter here. And this inverter can cancel this inverter, so it becomes N. Very good question. Yeah. Any question, guys? Here? So in the coming lab, you are gonna implement. So you are gonna implement a circuit, okay, using decoder. Yeah. Any question?
There's no lab.
No, no lab. Maybe more or after very soon.
This. You learn better.